The following content is provided by MIT OpenCourseWare under a Creative Commons license. Additional information about our license and MIT OpenCourseWare in general is available at ocw.mit.edu.
So last time we were talking about the general interactions that are present in a chemical bond, and we were in particular looking at the energy of interaction here as we brought two hydrogen atoms together. So we're looking at that energy of interaction as a function of the distance r between these two nuclei. And we saw, of course, way out here, the energy of interaction was minus 2,624 kilojoules per mole. As we brought the two hydrogen atoms in closer together, that interaction energy went down. It became a maximum negative value at some r. That r is the equilibrium bond length. And then as you try to push the two nuclei closer together, the energy of interaction goes up again. So far up that when you get them really close, the energy of interaction is greater than that of the two separated hydrogen atoms. And so in this region, the hydrogen atoms are no longer bound. So wherever this energy is lower than that of the separated hydrogen atom limit, you have a bound molecule. This was the attractive part of the potential. This was the well depth, or the bond dissociation energy measured from here to here. That's how much energy you'd have to put in to pull the two hydrogens apart. This is the repulsive region of that interaction potential. All right. We were talking about how that curve, that energy, was really the sum of three components. It was the sum, that energy of interaction was the sum of the nuclear-nuclear repulsion. That is, the repulsion between the nucleus of this hydrogen and the nucleus of that hydrogen. In addition to that nuclear-nuclear repulsion, there is the electron-nuclear attraction. The electron-nuclear attraction between the electron on the original nucleus, and when the two hydrogens get close enough, the electron attraction between the other nucleus. And then finally, there's the electron-electron repulsion. When these two hydrogen atoms come so close, the electrons now are going to repel. And so this curve is actually the sum of those three contributions. And what we were trying to do last time is to look at the dependence of these interactions individually on R. And then we wanted to sum them up to see why we actually have the shape of this interaction potential that we do. We're trying to decompose this. We're trying to understand over what regions of R which one of these interaction energies is dominant. Okay, that's what we were doing. All right. And I think last time we started in the sense that we recognized what the R dependence was for the nuclear-nuclear repulsion, right? The nuclear-nuclear repulsion is just the Coulomb interaction energy between two like positive charges. That nuclear-nuclear repulsion was E squared over 4 pi epsilon naught times R. And so that component I could easily draw. And I did draw it last time, I think. This is a 1 over R dependence, right? This is the E squared over 4 pi epsilon naught r. All right? So that was one of them. Now, next, these two terms. These two terms are what I'm going to call the electron interactions, because both of them involved the electron. This one didn't. This was just the nucleus. It turns out that I don't have a nice simple way to tell you what the R dependence between the nuclei will be for the electron nuclear attraction. Nor do I have a nice simple way to figure out what the R dependence will be for the electron repulsion. I can't do that without actually solving the Schrodinger equation. All right, so I don't have a simple way to break that down. However, what I can do is I can estimate what the sum of these electron interactions are at two extremes. Is this noisy? Can you hear me? Yes. Okay, I can see why it's noisy. It's got his thing sticking on it, which is rattling. All right. You might get somebody in there to try to fix that. Thanks. Okay. I do know what it is at two extremes. I know what those sums of those interactions are for very large R, and I know what it is for R equals 0. So what I'm going to do is I'm going to calculate it for R equal infinity and R equals 0, and I'm going to then put it on this plot, and then to just estimate what the R dependence is, I'm going to draw a line from that point to that point. That's the best I can do. Okay? So let's do that. Okay, let me start with this energy of interaction at R equal infinity. So I want to evaluate what the repulsive interaction is between the electrons at R equal infinity. What is that interaction energy? 0. It's 0 because the electrons are so far apart at R equal infinity that there's no interaction energy, right? It's the repulsive interaction. It's this kind of interaction. R equal infinity, hey, that's going to be 0. Good. But now, this term, this electron nuclear attraction, when the two hydrogen atoms here are very far apart, what is the energy of the electron nuclear attraction there? Pardon? I can't hear you, so I'll tell you. What it is the binding energy of a 1s electron, right? I mean, that is the energy of interaction. When R is very large, when R is infinity, the energy of interaction is just the 1s binding energy of the electron to each of its nuclei, right? The energy of interaction, the electron nuclear attraction, is just E sub 1s for this one and E sub 1s for that one, right? That's, in a hydrogen atom, that's what it is. It's the electron nuclear attraction. And so right here, this is equal to 2 times E sub 1s. All right? Now, you know that E sub 1s is equal to minus 2.18 times 10 to the minus 18 joules. But in kilojoules per mole, that's equal to minus 1,312 kilojoules per mole. And if we have two of them, as we do, well, 2 times E sub 1s is minus 2,624 kilojoules per mole. Okay, so I calculated what the electron interaction energy is at R is equal to infinity. So hey, that's way out here. So this is hydrogen plus hydrogen. This is minus 2,624. Same number I got over there. Okay. So now, what we got to do all right, so now what we got to do is we've got to calculate what that energy of interaction is at R is equal to 0. Well, when R is equal to 0, we have two hydrogen atoms right on top of each other, right? We've got two hydrogen nuclei right on top of each other. That means, in our kind of thought experiment here, that the charge on the nucleus is Z equal 2. That means when the two hydrogen atoms are right on top of each other, it looks like we've got a helium nucleus, right? And there's electron number 1 around it, and electron number 2 around it. Hey, that looks like a helium atom. All right, so now what is the total electron interactions in the case of a helium atom? What is the total energy of interaction there? Well, the total energy of interaction is going to be minus the first ionization energy. So this is going to be the energy of interaction of the helium. It's going to be minus the first ionization energy for a helium atom. Because minus the first ionization energy of the helium atom is the binding energy of the first electron to the helium. Right? Plus minus the second ionization energy of the helium atom. So in other words, if I have this one away, then the electron nuclear attraction between the helium nucleus and electron 2 is just the minus the ionization energy, the second ionization energy of helium. All right, does that make sense? You're too hot to think, right? Okay. That's what that is. And if you look them up, the total energy of interaction there is minus 7,622 kilojoules per mole. All right? Okay, so hey, I can plot that on this graph. At R is equal to 0. I got this, minus 7,622 kilojoules. So now I got 2 points. I got a point over here and a point over there. Hey, I'm going to draw a straight line between the two. And now, to get my total energy of interaction, I'm going to add this curve to that curve. And when I do that, give me some artistic license here, we're going to get something that looks like that. Okay? The bottom line is that this shape here is determined by the competition between the electron interactions, which are always attractive. They're always negative. The electron interactions are actually the sum of an attractive term and a repulsive term. But the repulsive term isn't so repulsive as to overcome the attractive term. It's always negative. So overall, even the sum is still attractive. All right? So the electron interactions are attractive. So this particular curve is a competition between the electron interactions, those attractive interactions, and the nuclear interactions, which are repulsive. In other words, you have to get the two hydrogen atoms close enough in order for the attractive interactions to take hold, but you can't get them so close Because if you get them too close, the nuclear-nuclear repulsions set in. So where your chemical bond length is determined by that competition between the electron attractive interactions and those nuclear-nuclear repulsions. All right? That's what determines the bond length. That is fundamentally here what determines the bond strength, is the competition between these overall attractive interactions due to the electrons and the nuclear-nuclear repulsion. All right? Okay, so that was the concept, really, that I wanted to get across here, was those fundamental interactions that make up this kind of curve. You're going to see this curve a lot. All chemical bonds have this kind of dependence on R, energy of interaction on R. Now, there's one other point I want to make, and that is that what we often and usually do is we reset our zero of energy. In other words, we're going to reset our zero of energy here so that the zero of energy corresponds to the separated atom limit. Why do we do that? Well, we do that because this energy difference, the minus 2,624, well, that energy difference was really the attractive interaction between the electron and its nucleus. It didn't have anything to do with the attraction or repulsion between the two atoms. And so when we want to talk only about the chemical bond and the energy changes when we make a chemical bond, it's often useful to shift our zero of energy down so that the separated atom limit is our zero of energy. And now everything that is negative relative to that is a bound interaction. When it gets too close, it'll be a positive interaction, and then the atoms are no longer bound. Okay? I mean, we're not forgetting about this energy here. We know if you're calculating the total energy, it's got to be there. But oftentimes, we just want to talk about the relative changes of the energy of interaction as a function of R when we're concerned only with forming a bond. Okay? Make sense? Okay. All right. So that's the general phenomenon. Now, okay. I'm going to take your ear for a moment. Okay. So now, what I want to talk about is one very simple model for an ionic bond. This is a classical model. And the amazing thing about it is that this simple classical model does give us insight into the mechanism by which this bond is formed. It is a mechanism that's only going to work when you form a very ionic bond. All right? So this is particular for a very ionic bond. And we want to take a look at this mechanism because it's going to give us some insight into how the bond is actually formed. Okay. So we're going to look at the formation of sodium chloride here. So we have a sodium atom and a chlorine atom, and they're coming together. They're moving toward each other. Well, what happens is that at a certain distance from each other, the sodium atom, believe it or not, actually ejects an electron. And that electron hooks on to the chlorine. And when it does that, well, then, of course, the chlorine now becomes bigger than the sodium. But now we've got two charges separated, a positive and a negative ion. And hey, there's a large attractive interaction between those two. So what happens is that these two ions are attracted into each other. They're just roped right in. All right? It's called the Harpoon Mechanism. Why is that? Why does the sodium and the chlorine just pull right into each other? Well, because of that rope. That rope is that Coulomb interaction. Okay? So this really happens. At some distance, the sodium atom ejects that electron, and then that sodium just pulls that chlorine right into it till it gets close enough to form a chemical bond, and you've got sodium chloride. This is a reaction mechanism that was elucidated many years ago, called the Harpoon Mechanism. It is a mechanism elucidated by Dudley Hirschbach, who's here at Harvard in the chemistry department, who has since retired, John Polanyi, who's at Toronto, Yuan Li, who was at Berkeley for most of his career. They received the Nobel Prize for this discovery of this mechanism and many other kinds of mechanism and dynamics of the reaction of chemical reactions. Yuan Li right here, this gentleman was actually my PhD thesis supervisor at Berkeley. And so so this is a simple picture, and this is exactly what's going on. Now, this seems a little strange to you, right? So let's try to understand exactly how this is working, all right? Okay, well, to understand this, what we're going to have to do is to look at the energetics of the system. And now I'm going to erase the screen here, I think. No, I don't want to. I'm going to raise it a little bit. How's that? Okay. All right, so what we're seeing is this gas phase sodium atom is ejecting an electron to form this gas phase sodium ion plus this electron. And of course, that's going to cost energy. The energy change is the ionization energy, which is for sodium 496 kilojoules per mole. Right? But at the same time, that electron is being caught by the chlorine. And when a chlorine and an electron recombine to form the Cl- gas phase, there's an energy release. As we saw, that energy release is minus the electron affinity of chlorine. That's equal to minus 349 kilojoules per mole. All right? So overall, going from a gas phase sodium atom plus a gas phase chlorine atom to a gas phase sodium ion and a gas phase chlorine ion, the overall energy change here, which is now the ionization energy minus the electron affinity, that overall energy change is 147 kilojoules per mole. Okay? So although we get some energy back when that electron attaches to the chlorine, we don't get enough energy back to compensate for having to pull the electron off of the sodium. So right now, this still looks like an overall endothermic reaction. We got to put 147 kilojoules into the system to make it go. So it's beginning to seem a little peculiar. How does this work? Well, we have to remember that, okay, all right, thanks. We have to remember now that once we make that sodium plus and the chlorine minus, that there's that Coulomb interaction. Right? The Coulomb interaction, bringing the sodium ion plus the chlorine ion together to make the sodium chloride, that delta E, that energy change, if I take two ions, sodium and chlorine, in from infinity and bring them together at the bond length, that energy change is minus 592 kilojoules per mole. So if I add up all three reactions to get sodium gas plus chlorine gas to make sodium chloride in the gas phase, the overall energy change there is minus 445 kilojoules per mole. And of course, the reaction is downhill. All right, but that still doesn't give you a really good feeling for what's really going on here. So to do that, let's look at an energy level diagram. Okay, so I'm going to kill the front lights. This is going to be back and forth here. All right, so what have I drawn here? I've drawn here the energy of interaction between a sodium atom and a chlorine atom, just like I did for hydrogen. I said all chemical bonds have this same shape of energy of interaction. Here's the bond length, right? 2.36 angstroms. Here's the well depth, or the dissociation energy. In this case, I show it measured from here to there. So it's minus delta E sub D, minus 445. Here, I set the zero of energy at the separated atom limit, sodium plus chlorine. Okay? All right, now, when sodium and chlorine are way out here, when R is really large, we saw that it's going to take 147 kilojoules to make a sodium ion from sodium and a chlorine ion from chlorine. Right? That's what I calculated right here. If the two are far apart, if you pull an electron off of sodium and put it onto chlorine, it's still going to require energy, 147 kilojoules per mole. However, I also said that when the sodium and the chlorine come close enough, the ions are pulled in close enough such that they can form a chemical bond, the energy you get back is 592 kilojoules per mole. On this diagram, where is that? Well, that's this energy, right? From up here to down there, that's 592 kilojoules per mole. Where did I get that number, 592 kilojoules per mole? Well, I calculated it. I calculated it using the Coulomb potential energy of interaction, which I'm calling here U of R sub E, at this value of R. The Coulomb potential energy of interaction, here it is, right here, right? For a point charge, if you treat the sodium as a +1 charge, and you treat the chlorine as a -1 charge, so all of a sudden we're forgetting everything about the other electrons. We're just treating sodium ion and chlorine ion as 2-point charges. If you forget completely about the other electrons and just treat them as point charges, that's the interaction energy right here. And that 592 comes from taking that expression and plugging in 2.36 angstroms. All right, so that's how much energy you get back. Okay, so now we understand the energies a little bit, but we still don't understand exactly how this electron jump process is happening, right? Because the way I've got it drawn here, it still looks like we have an electron jumping from sodium to chlorine way out here, and we have to put in 147 kilojoules before we get any energy back. Well, that's not the case. And that's not the case because of this. This blue curve here, this blue curve is just the Coulomb energy of interaction. We evaluated that point, that number from here to here using this expression. But you know that this is a minus 1 over R dependence. So if you're way up here and you treat this as a zero of energy for two separated, a plus charge and a minus charge, 1 over R kind of looks like this. That's the blue curve. Okay? All right. But you also notice that right here, you see that that Coulomb interaction is intersecting with this interaction potential between a neutral sodium atom and a neutral chlorine atom. Right in there. Right at this value of R, which we're going to call R star. The potential energy of interaction from here to here, right, is equal to the sum of this ionization energy minus the electron affinity. Right here, the electron can jump without having to put any energy into the system. You're close enough for the electron to jump, right? Because that Coulomb interaction has gotten lower, and it's at right that point when you can have that electron transfer and not have to put any energy into the system to get it to go. All right? So, in other words, right here, right, the energy from right there to this point is minus E star 4 pi epsilon naught, minus E squared 4 pi epsilon naught R star. All right? That energy, right at that point, is equal to, if I'm measuring here from the top now, minus the quantity ionization energy of sodium minus the electron affinity of chlorine. All right? So in order to solve for this distance R at which the electron jumps, at which that electron jump is energetically allowed, I'm going to set this equal to this. I know what the ionization energy and electron affinity of sodium and chlorine are. I know everything except R star. So I'm going to solve for R star. All right? So let's do that. I'm going to need the lights here. All right, so if I rearrange that equation, R star is equal to E squared over 4 pi epsilon naught times the ionization energy of sodium minus the electron affinity of chlorine. Okay? I know what E star is. It's 1.602 times 10 to the minus 19 coulombs squared. I have a 4 pi epsilon naught. I know what epsilon naught is. And then the difference between the ionization energy and the electron affinity I calculated over there, that's 147 kilojoules per mole, or 1.47 times 10 to the 5th joules per mole. Okay, but now, and this is what everybody forgets on an exam, all right? I have to calculate R star per molecule, not per mole, because per mole doesn't make sense. And I got this energy written here per mole. So I need an Avogadro's number up here, 6.022 times 10 to the 23rd per mole. All right? Don't forget Avogadro's number when you calculate R. So what's our star? Our star comes out to be 9.45 times 10 to the minus 10 meters. Okay. So let's get a perspective on these distances. The sodium atom here, that sodium atom, diameter 3.8 angstroms. Chlorine atom, diameter 2 angstroms. What I'm saying is that this electron can jump, or does jump, from sodium to chlorine at this distance, R star, which is equal to 9.45 angstroms. Okay? So the sodium and the chlorine really are a considerable distance apart when that electron jumps. But that electron can jump because it is at that point that the Coulomb interaction is large enough here, right, to compensate for the difference in the ionization energy and the electron affinity. And this actual number here was verified in these experiments by Hirschbach and Lee. Right? It actually does happen. And this very simple model, classical model, where we're actually treating the sodium and the chlorine as point charges. We've forgotten everything else about the electrons. Hey, that works remarkably well. All right? Now, what this model doesn't give you very well is the bond energy. All right? Because if you look at this diagram again, right in here, oh, let me go back one here. If you look at this diagram, this 147 kilojoules here, well, that I can look up. This 592 kilojoules, well, that's just the Coulomb interaction between a positive and a negative charge at 2.36 eV. That's all that is. You can calculate that. And so therefore, if I want to calculate the bond energy of sodium chloride, right, the bond energy is just the difference between this energy and that's 445 kilojoules per mole. Well, that doesn't come out so well in terms of the actual bond energy. The actual bond energy is 412 kilojoules per mole. And we know why that didn't come out too well. And that's because this depends on all of the interactions that are much closer in to the nucleus. By the time you get down here, right, the repulsive interactions are present. The nuclear repulsions are present. And in our simple model, we didn't take that into account, the nuclear repulsions. This simple model worked to get our star because our star is further out. You know, the nuclear repulsions haven't really set in yet. And therefore, the simple model works when you're at a far distance, when R is large. But to get the bond strength here, you're much closer in. Right? You're at 2.36 angstroms. That's the difference in energy from here to there. Hey, we forgot about the repulsive interactions between the two nuclei. So the model isn't going to work so close into the nucleus, but it does a really good job of getting our star far away from the nucleus. Now again, this simple model only works for very ionic compounds, very ionic bonds like sodium chloride. It won't work very well for hydrogen chloride, for example. All right? Okay. Questions on that? Yes?
When you do like these energy transfers,
Yes.
what will be the final
All right, we're going to deal with entropy and Gibbs free energy changes in a week or two. Right now, what I'm writing here are energy changes. And so I'm actually dealing with single molecules. I might have in my mind here writing the energies per mole. But what I'm thinking about is not an ensemble of molecules. I'm actually thinking about what's happening in each individual single molecule interactions. That's why I haven't talked about delta G here at all. Okay? And in chemical dynamics, that field of chemical dynamics, that is where we want to look at individual events as opposed to a Boltzmann average of events. Okay? So that's what I'm talking about right here. All right, but we're going to talk about collections of molecules and the energy changes. I'm going to change my definition from delta E to delta H, the bond enthalpy, in a couple of days or so. Okay? Other questions? Okay. Well, there's one other just rather brief topic that I wanted to talk about, and that is calculating dipole moments, or measuring dipole moments, and then from the dipole moments getting out some ionic character to a chemical bond. So your book actually calls ionic bonds, calls them polar covalent bonds, and that's fine, because even a very ionic bond like sodium chloride isn't completely ionic, in the sense that when it's the molecule, you know it's not a point charge on sodium and a point charge on chlorine. You've got an electron distribution, right, when you're that close. And so what you've got in an ionic bond or a polar covalent bond here, what you have is an asymmetric charge distribution. You know, in an HCl here, you've got both electrons on the average being closer to the chlorine nucleus than it is to the hydrogen nucleus. And you have that because you have a bond between atoms with two very different electronegativities. So that's a polar covalent bond. Now, what we're going to do is we're going to use this symbol delta here as a measure of the amount of electron transfer. So delta is the fraction of a full charge that's asymmetrically distributed. So this plus delta, or this delta that was on the hydrogen is now on the chlorine, is the interpretation of that symbol. That asymmetric charge distribution leads to a dipole moment. A dipole moment is defined as Q, where Q is the magnitude of the charge separation, times R, where R is that charge separation. It is, strictly speaking, a vector. All right? Q times R is what we define as a dipole moment. The units of dipole moment is coulombs times meters. You can see that from Q times R. Dipole moment is also a vector. I have the vector on this slide going from the positively charged end to the negatively charged end. That's the way your present book does it. In your notes, I have it reversed. I have it reversed because the last time I taught this, I was using a book that used a different notation. And I sent it out for Xeroxing before I realized this was different. So change it around. Not that it's ever going to make any difference. Okay, but your book has this convention, from positive to negative. Okay. Now, this unit, though, of a Coulomb meter is a very large unit, an inconvenient unit. So we got another unit. It's called a Debye, named after Peter Debye, who first studied these polar covalent molecules. And a Debye here is defined as the following. It is defined as if you have a full unit charge now, not a delta, a full unit charge, moved from here to here, and the charge is separated by 0.208 angstroms. That defines this unit called the Debye. All right? So they're 0.208 angstroms per Debye. So if you knew the fraction of charge that is separated, and you knew the bond length in angstroms, and then you have our definition for a Debye, which is 0.208 angstroms per Debye, you could calculate the dipole moment in Debye. But usually what we do is not to calculate the dipole moment. We usually measure the dipole moment and calculate the partial charge distribution. Because we usually don't know this. We can measure that. We can measure the dipole moments in a kind of capacitor arrangement where we have some molecules that have a dipole moment, positive charge on one plate, negative charge on the other. And when you do that, of course, these dipoles are going to align. These electric dipoles are going to align. That's going to change the capacitance. If this capacitor is part of a resonance circuit, it's going to change the resonant frequency. The resonant frequency is related to the dipole moment. And in that way, you calculate the dipole moment or measure the dipole moment. And that's how it was originally done. However, you can now measure dipole moments very accurately by rotational spectroscopy. And we're going to look at that in a few lectures or so. But take HCl right here. Here's HCl. Here's the measured dipole moment. Here's the bond length. We can use these two pieces of information to calculate the fraction of charge distributed. And in the case of HCl, that is about 0.18. Sometimes we refer to this in a percentage. So this would be 18% of a charge separation. Sometimes we say 18% ionic character in HCl. That compares to something like 70% or 80% in sodium chloride or lithium fluoride. So HCl isn't anywhere near as ionic. The charge distribution isn't as asymmetric as it is in sodium chloride or lithium fluoride. Okay. All right. Thank you very much for hanging in here today. It's been hot. Have a nice, cool weekend. See you next Wednesday.